Hi class, welcome back to multivariable calculus. Today we have a really short lecture on path dependence and how to tell whether a vector field is a gradient field. So we looked at this a little bit last class, but we're going to just expand on it today. And so we can test whether or not a vector field is a gradient field, in other words, conservative, by computing the partial derivatives. So the vector field f is equal to f sub 1 I hat plus f sub 2 j hat is a gradient field if and only if del f1 with respect to y and del f2 with respect to x are equal to each other. So let's just start by jumping into an exercise. We are going to determine whether the given vector field is a gradient field. If it is, then we're going to find the potential function, f of x and y. Otherwise, we are going to explain why the vector field is not a gradient field. So our first one we're going to look at is our vector field is equal to x sine xy I hat plus y sine xy j hat. All right, so beginning with del f1 over del y. Okay, so taking the partial with respect to y for this first piece, we are going to get x squared cosine xy. Remember, this is with respect to y. And if we took del f2 over del x, we are going to get, well, once again, the derivative of sine is cosine, and then we have xy inside, but we're taking it with respect to x, and so we end up with y that we're going to bring out in front. So we have y squared cosine xy. And of course, it's clear that del f1 with respect to y is not equal to del f2 with respect to x, so we can conclude field f is not a gradient field. So it's not conservative. All right, let's do a couple more. So let's look at another one. The vector field is going to be cosine y minus y I hat plus minus x sine y minus x j hat. So del f1 with respect to y is going to be minus sine y minus 1 and del f2 with respect to x is going to be equal to minus sine y, since just derivative of x with respect to x is 1 minus 1. So here we have del f1 over del y is equal to del f2 over del x. So therefore, our field F is a gradient field. All right, and so now let's go ahead and find the potential function. So first, we're going to want to integrate f1 with respect to x, which is going to give us x cosine y minus yx plus g of y. And then we're going to take the partial derivative with respect to y of x cosine y minus yx plus g of y, which is going to give us minus x sine y minus x plus g prime of y. All right, and actually this gives us fully our f2 right here. And so this tells us that g prime of y is going to be 0. And so our full function is, our potential function, f of x and y, is going to be x cosine y minus yx plus whatever constant you want. Okay, so that's it for that one. So that's our potential function for our gradient field. And let's look at one more. Okay, and so for this one, let's look at our field F is going to be equal to the natural log of y I hat plus x over y j hat. All right, so del f1 over del y is going to give us 1 over y, and del f2 over del x is going to give us 1 over y. So this tells us that field F is a gradient field. So now let's go forth and find the potential function once again. So we have the integral of f sub 1 dx, so ln, the natural log of y, dx is going to give us x times the natural log of y plus our constant g of y. And so then if we take the partial derivative of this with respect to y, we get x, we have the partial derivative of x times the natural log of y plus g of y. And that is going to give us, our first piece is going to be x over y, because the partial of del the natural log of y over del y is going to be 1 over y times x plus g prime of y. And so that tells us that, once again, this is our full f2, so g prime of y is 0. So our potential function is going to be x times the natural log of y plus whatever constant you want. All right. And of course, there's a constant in there too, or in my case, let's just say my constant is 0. Okay, so that is all for today. I told you nice and short. Next time, we're going to have a longer lecture on Green's theorem, and that's going to be our final lecture for the semester. So I will see you then.